Hi, and welcome to this STAIR Tailored. I'm Erica Mason from the University of Missouri. What you're watching today is part 3 of a 5-part video series in which we talk about how to factor quadratic expressions. Today's video is about how you can encourage students and give them the opportunity to discover the rules about factoring these expressions. Before we get started, let's talk about the underlying concept for what this work is built upon. So you'll see here, these are the 3 most common types of mathematical representations: concrete, pictorial, and abstract. You may also have heard this referred to as concrete, representational, and abstract, but those are just the same words, different words for the same concept. In her 2017 article, Tricia Strickland describes the benefit of using multiple representations in order to understand algebraic concepts. In particular, she reminds us that the 3 types of representations really don't exist in a hierarchy, but in fact, they can be used interchangeably and flexibly. So the goal here is to support students in becoming proficient in using all 3 types of representations so that they can ultimately choose which one makes the most mathematical sense to them. This is especially important for students with disabilities or who have mathematics difficulty, so that they can, again, have multiple opportunities and multiple entry points into tasks and other mathematical problems. We're going to turn now to the document camera, and we're going to do some work on how discovering these rules can look in your classroom. So first, it's important to understand that this task was designed so that students discover the rules. That is, instead of telling them these are the rules to factor expressions, we're actually going to let them have the opportunity to explore and create and to come up with an understanding all on their own. So what you might do is you might first start by giving them these 2 expressions here. You might ask them to represent these expressions in whatever ways make sense to them. So they might choose to use algebra blocks like we've used here, or they might choose to use a drawing. Either way, you're going to give students the opportunity to represent these expressions. Once they're represented, you might then ask students to find out or to derive the factors that go with each of these expressions. The expressions here actually represent the product or the answer, which is represented inside the corner piece. So once students have come up with the factors, right, for each expression, this is a great opportunity then to start asking students some really intentional questions. This is a really good opportunity to say that this lesson or this series of lessons might take multiple class periods to cover. It's totally normal and expected that students are going to really explore and engage deeply with this content. So don't be surprised if you introduce these concepts and they take 1, 2, or even 3 class periods. The goal, again, is for students to discover these factoring rules on their own. And in doing so, they're really going to walk away from this experience with a deep and rich understanding about what all of these mathematical concepts are about. So once students have represented their expression, they've discovered these factors that go with each expression, you're now going to ask them a series of really thoughtful and intentional questions. So when looking at these 2 examples, you might ask students, what do you notice about the shape of the rectangle as we add a constant term? When the question refers to a rectangle, we're really talking about the product or what exists inside the corner piece. So you're asking this question and you're drawing students' attention to how the product or the rectangle changes as the equation changes. Even though at this stage in learning, you would not introduce the rule to students, and it would be really unexpected that students would have discovered the rule by now, we wanted to give you the opportunity to see the rule in this example. Ultimately, the rule that we want students to arrive at is this. In order to get this expression, you have to attend to the 2 factors, specifically these constant terms. So you're going to add these constant terms to get the linear term, and then you're also going to be able to multiply these constant terms to get this constant term. Again, this is a rule that we expect students to learn after much effort and trying and after many examples. And so we just wanted to share that with you at this point in our lesson. But again, don't expect students to arrive at that understanding at this point. So here's another set of problems that you might offer to students as they're going through this exploration of discovering the rules for factoring these expressions. Here again, you have these really similar expressions, and once students represent them either using these concrete manipulatives like algebra blocks or through drawing, you're then going to ask them to consider this question. What do you notice about the shape of the rectangle when we change the middle or linear term? So again, you're asking students to sort of look at their representation and compare what they notice, right? So students are going to make all kinds of observations at this point, all of which is in service of leading them to understanding the larger rule that's happening here. In addition to these problems that we've asked that are specific to these represented problems, you can also ask students to sort of ponder some scenarios that are separate from these representations. So for example, you might just pose the question, is the value of x squared plus 7x plus 6 greater than or less than x squared plus 7 squared plus 12 when x is positive? So you're asking students to, again, think about the relationships that exist between linear expressions, but now you're moving away from them using these representations and you're just asking them to reason more broadly. Another question you might ask is there a greater increase in overall value when we increase the constant term or the linear term? So here, students might be tempted to do some guessing and checking, or just some experimenting in which they plug in different values for x and then compare what happens when they adjust the constant term or the linear term. Once students, again, have represented these expressions, and then once they've derived the factors from these expressions, you can again then reinforce this rule, or I should say that the rule itself will be reinforced over time when students come to see that when you attend to these integer constants here in the factors, that you should be able to add these constants in order to get this linear term. You should also be able to multiply these constants to get this constant term. Another way of checking and sort of making these rules really salient to students is to draw their attention back to the representation they made. So if these are all true, they should be able to see the mathematics in the representation. So again, let's think about that rule. We're going to look at these integer constants, 2 and 3, and we're going to ask ourselves, can we add these integer constants to get the linear coefficient? So in this case, it's 5. And do we see 5 x's represented? Well, we do. 1, 2, 3, 4, 5. You can also check by asking whether or not you can multiply these integer constants to get this constant, which in this case you can. 3 times 2 is 6. Thanks for watching this STAIR-tailored video. Stick around for our next video in which we introduce a graphic organizer, or the box method, that students can use to factor quadratic expressions.